So in today's class we'll continue with 8255 programmable peripheral interface, which I introduced in the last class. So this is the summary of what we did in the last class. We said there is an 7-bit control bit through which we can program 8255. The first bit is the most significant bit is D7. If it is 0, then it is known as an then the C port we can program it bitwise, right? If it is an 1, the most significant bit is 1, then the 8255 all the 3 ports would work like an unique ports, that is an 8-bit ports. Okay, so if it is 1, right, and then again within IO port it can work as mode 0, mode 1 and mode 2. In mode 0 you will have all the 3 ports working as 8-bit ports. Okay, the simple 8-bit ports. If it is and then if you can program it as mode 1, you can either program port A as mode 1 or port B as mode 1, or both the ports as port 1. In that case, some additional lines from C for port A, the higher bits 4 pins of port C also will be used along with the 8 pins of port A, and these 4 additional lines will be used for handshaking, right? And if you have port B programmed as mode 1, then the lower 4 pins of port C also will be used along with port B for handshaking, right? And then you have something known as mode 2. In mode 2, all the 8 lines available of port C will be used for handshaking signals. In this case, mode B will be left with only with option of mode 0. Okay, so this we saw in the last class, and today we will see. I will take up one example first. Okay, so the problem is like this. We need to read the condition of the switches from there are 8 different switches, so 12 different switches. So obviously you can't connect it in a single port. So we have these switches connected from A0 to A7, that is the 8 pins of port A, and also the higher port C pins, 4 pins, we have taken it as again input. Okay, so these are also the 4 input signals which we need to read. Okay, so this forms the 12 input pins total, and then accordingly we need to light the LEDs. So you have total of 12 LEDs. Again you have 8 pins of port B connected to these LEDs in this configuration, and then you have additional 4 from the PC 0 to PC 3, that is the lower half of the port C, that is also used as now as an output pins. Okay, so these are output pins, or these are the input pins. So if you see here, if the switch is closed, it will be reading a 0, that particular. So if the switch is open, you have 5 volt going into these pins. Okay, so whenever the switch is closed, then that you are switching on the light actually, so but it is active low. So whenever you are switching on the light, a 0 will be red. If the switch is off, and 1 will be red, and the outputs are also active low. So if it is a 0 out here, the LED will glow, right, because you have given you have connected the 5 volt to the anode of all these diodes, and the cathode is connected to the port pins. Okay, so if whenever there is a 0 available here, a current will flow from 5 to 0, and then the LEDs will glow. And if it is the output is 1, then you have 5 volt applied across both the cathode and anode, so no current can flow in through the LED, and so it will not glow. So both the switches as well as these LEDs are active low. So we need to read these data from these pins, and then accordingly give the output in these pins. Okay, so it is given that the base address is 00. So the base address is 00 for this port. Okay, so the first and foremost thing is we are going to declare the address for all these port A, port B, port C, and also for programming. So we know that port A stands for 00. The base address is 00, so we don't have to worry about that. So it is 00. 02 is going to be for port B, 04 is going to be for port C, and 06 is going to be for the internal register, the control register. Okay, so these we are named these as variables: C register, port A, port B, port C, right? And first thing we need to program this 8255 for the required mode of operation. So we need to put some data into the control register. So what is the data? So this is what D7, since it is input output register, so this is going to be 1 out here, so it is 1. So the next two pins are for the mode, for port A mode, right? And that is going to be 0 0, because we are going to work in mode 0, right? So this is put as 0 0 out here. Okay. The next one is whether is port A, whether it is input or output. So 1 stands for input, and we know that 1, so hence we have written here 1, because A we are going to configure as an input pin. Okay. Then the next one is port C upper, whether it is going to be an input or output. So if you see the figure here, port C upper is also we are going to use as an input signal. So that is the reason it is put 1 out here. And then port B mode, that is going to be 0 here, right? And the next one is port B, whether it is an input and output. Now here port B we are going to use that as an output, and port C lower is also output. So the last two are 0 0s. If you see here, port B and port C are output. So that is the reason, sorry, that is the reason this is 0. So hence this is the binary bit series which we are going to put into the control register. Is it clear, this, to all of you? Okay, you might have some problems like this in your exam, so you should know for different mode of operation how to write this control bit. Is it clear to all of you? Okay.
So why are we doing the rotate operation?
Yeah, I have not yet come to that place, right? Okay, I am going to come to that. Okay, so this is the we have just configured now and put this value into the register for the mode of operation. Now we need to read the data from port A first. Okay, so these are the from the port A, and feed the data to port B. Okay, we'll see. Then we will read the data from the upper half of the port C, and then put it into the lower half of the port C. That also we will do it too. So first we read it in port A. So the data of port A, so will be available in AL register, and then out port B. So whatever is there, so according to the position of the switches, okay, the LEDs in port B will glow. Now we are going to read the in port C, okay, into the AL register. We are going to read. So the upper four bits, okay, the second nibble of port C, okay, that data will get that data will get updated with the position of the switch, whereas in the lower nibble of the AL, okay, you will have the first four bits of the AL. It will be junk data, because we have just taken input from port C, and in port C, if you see, the only 4 lines are connected. Sorry, here only 4 lines are connected. The others are configured for output. So if you try to, it will try to read. It will try to read from these points also when you are giving a command like that to read. But then, since it has not been configured for as an input, so some junk data will be put into that 4 bits. Okay, now I have to, but now I have to feed put the output data into that 4 bits. Now the lower 4 bits. So we know that rotate command, where we can rotate and move, but we have to rotate it 4 times, right? So that is the reason. Now before that, to eliminate that junk data and to put 0 0 there, we can do AND AL F0, right? So we know what an AND operation does. F means for the first most significant bits will be 1 1 1 1. So that data will be preserved as such, and whatever was the junk data, that will become 0. Then you write move CL4, that is essentially when in the next step we are going to rotate it 4 times. So that is the reason we have put 4 here. We rotate it 4 times, and then out and a port C. Now when we write out port C, okay, the lower 4 nibbles, we have got whatever is the data we read from the port C here. Okay, that from the higher port C, that data is now available in the lower port C, and that goes, and according the LED lines, LED lights will glow. Is it clear, Ruben? Rest of you?
So could you explain what happens when we do the rotate operation?
Rotate operation is like from the MSB it will go to the LSB, and everything will rotate once, right? Rotate right, it is ROR.
Yes, sir. But I mean, why are we rotating to the right? Why are we shifting all the bits to the right?
Because when once we have read these four datas, okay, in the AL register, initially the input is coming from the higher four bits, like only 4 bits we are reading, right, from from C4 to C7. Okay, so in the AL register, from no, bit 7 to bit 4, you have some data which has been read, whereas in the lower bits of AL there is no data, it is junk data. So we are going to first put 0, but when I am putting writing an out command, right, that is from 0 to 5, 0 to 3. Is it understood?
Yes, sir.
Okay, this C port is an 8-bit data. We are reading from the higher 4 bits and giving the output to the lower 4 bits.
Yes, sir. Got it.
Okay, so that is the reason we have to write this rotate. Okay. Now, we'll see what are the handshaking signals. So in the handshaking signals, so I said 4 more lines will be used for handshaking. So whenever we have an input read to be done, then the input output device first places a strobe dash signal. Okay, that is a signal which is placed to 8255, telling ki okay, I have something to be transmitted. Okay, so based on that strobe signal, right, if you see, the 8255 will, since it has placed a request, it will say buffer full signal. Okay, it will give an buffer full signal to the input output device, input buffer full signal. That means you can place your that will be placed once it has this will the 8255, the input output device will place an interrupt signal, okay, to the 8255, and place the data which is required to be transferred. Okay, so the data lines also it will place an data. So once this data is read by 8255, it will say okay, buffer full signal. Okay, I have acknowledged your interrupt and read the data into my buffer. Okay, it will say the buffer is signal. So this buffer signal, it will be given to the input signal out here, right? And also 8255, after taking this data into its buffer, it will send an interrupt signal to the microprocessor. An interrupt signal will be sent here, right? Okay, and when you have, once that interrupt signal is sent, okay, 8255, whenever it sends an read bar signal, that means okay, once it has sent an interrupt signal, 8255 will subsequently decode the interrupt request based on the vector table, and then it will go and finally when it will understand okay, some data is to be read, it will send the read signal, low signal, okay, to the 8255. Once that signal is acknowledged by 8255, it is received by 8255. Okay, then the new data, it is understood that okay, the data has been read by the microprocessor. Now the interrupt and request signal will go low, and also the buffer signal also will be low, and everything will be reset as it is. Okay, so these are the handshaking signals which happen between the input output device and the 8255 and the 8086. Okay, so if I repeat it, initially the input output signal, the input output device will ask that okay, I want to transfer some data, so it will a strobe bar, it's a strobe bar, it will send a kind of interrupt signal to 8255 telling that I want to transfer some data, and it will place that data onto the data pins lines, 8 lines which is connected between these are the port lines between these are the additional lines which are taken from the port C. This is the data line which is already there between either it could be port A. This could the same happens with mode 1 in port B also. Here in this case we are discussing with port A, that is why it is written port A to P0 to A0 to A7. So the data will be placed here. Okay. Then the next step is, okay, once it has placed the data, it will be written into the buffer of 8255. So once the input buffer data is available, it will generate an input buffer full signal. Okay. Followed by it will send an interrupt signal. Once the input buffer is full, it will send an interrupt signal to the 8086 that, okay, one of my input output devices is ready with some data to be communicated. It will send an interrupt request signal. Okay, so 8286 will service that interrupt service. Okay, and then subsequently when it is ready to read the signal, it will send an ready bar, okay, signal. Okay, once that is sensed by 8255, okay, so the input, now since that data has already been service read into the 80, the buffer signal will go low, okay, indicating that, okay, the input output device can now again make one more request. Okay, only this will make a request only if the input buffer signal is low. Okay, so because it is high here, the input output device in this condition will not make one more request. Okay, it will, since it has gone low now, after the microprocessor has read, the signal has gone low, indicating to the input output devices, okay, if there is a requirement, you can make one more request. Okay, so this is the handshaking signals in the read mode. Okay, in the write mode, everything gets initiated from the microprocessor side. So now whenever the microprocessor wants to write a data, the first thing is the microprocessor will send the write low signal. Okay, so when it is sending a write low signal, okay, so the data will be placed by the microprocessor onto the data bus bar here, out here. Right. So once it is placed the data once it gets loaded onto the buffer of 8255, now the 8255 will send an output buffer full signal, low signal. Okay, so output, and also it will send an and it also the interrupt signal will go low out here. Okay, so based on this write signal, okay, the interrupt signal will be disabled here. Right, so that now it is indicating that this signal is not available right now, because there is already some action taking place between the microprocessor and 8255. Okay, now this data is available in the buffer full out here. Right, okay, this signal is gone here, and whenever the input output devices captures this data, okay, into its this data which is available, it will send an acknowledgement signal. Okay, this acknowledgement signal. So this acknowledgement signal, the input output device sends to 8255 that, okay, whatever data is available in the output buffer, I have read that. Okay, I have read that. So this is indicating, okay, now you can go ahead and remove the data which is available in the data bus bar, and hence the interrupt signal will again go high. Okay, indicating that, okay, now that will indicate to the 88 microprocessor also that, okay, this data whatever you had sent, and that has been returned into the input output device. So this is the sequence which happens during an output write. Okay, so if I repeat it, initially 8086 will initiate a output write, so the write signal will go low. Okay, so once it goes low, it will also place the data which is to be written onto the bus bar, onto this bus bar. Okay, it is, so once this data is available, 8255 will replicate that data through a buffer. Okay, so once that data is available in the buffer, this buffer signal will go low. Right, and also the interrupt signal will go low here. This interrupt signal will go low here. Right, in case it is 1 also, it will go low here. Okay, so that and then you have this data. Now this data is available into the input output buffer. Right, okay, this data is available here, and you have placed a signal that data is available in the output buffer. So input output device will read that data. Once it has read that data, then it will send an acknowledgement signal that okay, I have read the data. Okay, based on that acknowledgement signal, an interrupt signal is sent to 8086 telling that okay, the data has been read and you can move ahead and do the next instruction, you can execute the next instruction. So an interrupt signal will be sent to the 8086. Okay, so this is how the handshaking happens in output signal. Okay. So this is known as mode 1, strobed input output. That is what we said. There are two groups are available for strobe. Each group contains an 8-bit input output port and 4-bit control data bit. Okay, so the additional 4-bit is taken from the C port. Okay, both the inputs and outputs are latched. Okay, it is going. So in here you have an latch inside this, so that a latch and a buffer. And so that the data is latched out here. Okay, and then it is transmitted out here. So you have an latch out here. Out of the 8-bit port C, P0 and to P2 are used to generate control signals, for that the lower ones are used for port B and the higher ones are used for port A. Okay, and also these signals are used as independent data lines also, P6 and P7 during these modes of operation. Okay, mode 2 is bidirectional, in which all the ports of it's an on 5 bits are used as control pins instead of 4 bits, and additional 3 pins are also used for some accepting for some data transfer related to handshaking between these two 8255 and the input output ports. Essentially, all the 8 pins of port C will be used along with the 8 pins of group A in mode 2. Okay, you need to remember that much. Okay, so port C will not be available totally. Once you have configured it for mode 2 operation of group A, you can't have port C. All the port C 8 pins will be used by group A itself. Okay, port A itself, along with its own 8 pins for data transfer, and all the handshaking signals and the rest of the lines will be used by the group A. Okay, so these are, now we said there is one thing which we left out was I said each of the port C lines we can program individual pins also as a single output or input line. Okay, for that the first bit in the control this has to be set to 0. Okay, if it is set as 1, then port A, B, C are going to work like a normal 8-bit port. Okay, but if you are going to set it as 0 out here, in that case only port C, you will see each of the bits can be treated as an individual input or output. Okay, so this is the format in that case. If you put 0 out here, the next 3 bits are going to be don't care, and the next D1, D2, D3 will select which is the pin. Okay, 0 0 means C output port C pin 0, and 1 1 1 means pin 7. So accordingly, right, and then the last bit, if it is 1, it will be set to 1, and if it is 0, it will be reset to 0. So for example, if I write all 0 0 here, 1 here, okay, 0 means it is going to be C port is going to be this is the first command. This address, this data I need to put it into the control register. Remember, okay, this data I have to put it into the control register. Okay, so out this particular data, I have to use an out command, and this particular data and into the C6 in this case. If I go back, okay, let me go back there, and so that this, okay, into the register, C address corresponding to the 6. Okay, so we need to put it there. Okay, we can't address it to port C. Okay, so this data is not put, remember, it is not put into port C, although we are configuring this data we are configuring it for port C, but we need to put this data into the control register and not directly to port C. Okay, so the first bit will be 0, and here what happens is the PC 0 pin will be set to 1. Okay, in this command, if you see 111 is selected out here in these 3 bits. Okay, that means that pin number 7, okay, pin number 7 of port C will be reset to 0 since you have put a 0 here. In the third case, if you see, it is 001, that means PC 1 will be set. It is 1, it is set to 1. Okay, these are three different commands which we can put into the register, and accordingly the pins of port C will be no, output will be either 0 or 1. Is it understood, this aspect?
Yes, sir.
Okay. So, for example, so we'll take one more example, so it will become very clear. So, connect three LEDs to port C. Okay, blink one LED after another at regular interval of 1 millisecond. Okay, the base address is given 0 0. Okay, so how to do that? So we are going to connect three LEDs individually to port 0, port 1 and port 2. We have connected three LEDs. So to glow these LEDs, this has to be 0. This port, only this pin has to be 0, and then this pin has to be 0, and then this pin has to be 0. Okay, so initially it should be 0 1 1, and then wait for 1 milliseconds. Then it should become 0 1 0, and then wait for 1 milliseconds. Again it will become and then it has to become 1 1 0, and then wait for 1 millisecond. Okay, so that is how the cycle. Okay, 0 1 1, wait for 1 millisecond, then 1 0 1, wait for 1 millisecond, and then 1 1 0, wait for 1 millisecond, and then repeat the cycle. Okay, so that is what it has to be done. So we need to write a program. Okay, so the first one is, first we need to put some data into the control bit, right? So we know this is how, and so this has to be 0. And then configure these data accordingly. Okay, so let's take, we'll do it directly out here. Okay, first we are going to put an 0 6 into the control register. Okay, that essentially is okay, that is giving the address to the CR, control register 06. Okay, so that is, we are feeding the address into the CR register, and then the first we are going to move on all zeros into the, let me write the whole thing. Okay, okay, all zeros into AL. Okay, all zeros into AL, and then we are moving it into a CR. All zeros, what will it do? All zeros. Okay, if I go back, all zeros, if I put all zeros out here, okay, 0 means bitwise. Okay, 0 0 here means the bit 0 is going to get selected, and 0 means it is going to get a reset. Okay, so the first bit will have an 0 output. Okay, if I put all zeros, so what is going to happen? If you see here, 0 means bitwise. Okay, we are configuring it for port C bitwise. Okay, D2 to D3 D4 is 0. That means, okay, bit 0, and we are going to put 0 into that port. Okay, we are going to put 0 into that port, and this is also 0 because the D1, right? D0 is okay, yeah, D0 is 0. That means the output port we are going to get 0 here, right? So that LED will glow. Okay, and whereas, so the first, this LED will glow. This is the first two lines move AL 0 0. The first LED will glow, and if you see in the next command, we are writing move 0 3, and again moving the data to the output port, and 0 3, what will it do? If I go back here, 0 3 means this is going to get 3 means this is going to be 1, and this is going to be 1 out here, right? So this is going to be 0 0 1. That means the first pin, okay, the pin number 1 is going to get an 1 input. Okay, so if I go back here, this LED will be off because I am writing 0 3. If you write 0 3, okay, this is going to be 1. Okay, that is going to be, that means it is going to be a high output, so the LED will not glow because it is an active low here, and this is 1 means port 1. So the second LED is not going to glow, and in the third it is written 0 5, right? And if I go back here, 0 5, that is 1 0 1. So 1 0 means the pin number 2 here, this LED. Okay, 0 2. So that LED is not, now we are going to put 1 there. So the third LED is not going to glow here. right? So is this much part clear to all of you? Okay, if I write these three commands, okay, what it is going to do is it is going to the first LED, the topmost LED, which corresponds to port number 0, okay, pin number 0 of C port, that is going to glow, and pin number 1 and 2 is not going to glow. Okay, so that is how this we write this command, and then we call for an delay. Okay, delay is just we can we have read about how to introduce delays. So you can write a delay procedure. We move some count into CX register, no operation loop here where the value of the CX will reduce. So it will be in this loop for some time. So you can control this value which is there in CX register, so that 1 millisecond delay is introduced. Okay. So after having returning from the delay procedure, now in the next go we are going to write 0 1 into the move register, and then out CL. Now if you see here, now bit 0 we are going to put 1 here, so that LED will switch off, and in the next command you are writing 0 2. So 0 2, if you see, it is going to light up the second LED, and 0 5, this is going to keep the third LED off. Okay, again you call for a delay procedure, and then you again move 0 1 into AL. Okay, that is going to keep the first LED off. 0 3, it is going to switch off the second LED, and 0 4 now is going to switch on the third LED, the bottommost LED, and then you call for a delay, and then you do a jump repeat. Okay, is this program clear to all of you? Is there any doubts?
Yes, sir, understood.
Okay, so this is how bitwise programming. This is for the C port, individual bits, and we can change the data. Okay, so this is again, if you have to interface and data and a 7 segment display, again you can connect it into the port B, right? So whenever some binary data, BCD data is to be written, so you need to you can connect an 7447, okay, which will convert it from binary to 7 segment. It is a binary to BCD to, so BCD to 7 segment converter. Okay, so because the 7 segment display requires 7 different outputs, so that will be available from 7447. So this is just to give you an whenever you want to drive an 7 segment display, you don't have to write the entire code of converting the data into the 7 segment display format and then give it into the port to drive an LC. So you can use these kind of IC 7447. You can keep the data as it is in BCD format and use this external these ICs, which will convert it from BCD to 7 segment display drive, which can be used to drive an 7 segment display. Okay, so that's all. With that, we come to an end of this small capsule on 8255. In the next class, we will take up timers. Okay, so that's all for today. Next class, I think we are going to have after a long break. Saturday is an holiday.